At Golden Barrel Technologies, we believe learning should be practical. This video gives you a glimpse of our free VLSI internship where students present what they have learned and how we guide them. Instead of just theory, we focus on understanding, implementation, and confidence. Let's take a look at how our students are learning step by step. Okay, so Manish, you want to present?
Yes, sir, I'm going to present.
Okay, you can share the screen, you can present here.
Okay. From Guru Gobind Singh Independence University, third year student, BTech Electronics and Communication. So today my topic is VLSI Physical Design from Netlist to Silicon. So basically, in this presentation, I will explain the complete physical design flow in objective important step and why is important in the chip manufacturing. So evolution of VLSI. So first of all, we know about the VLSI. What is VLSI? In which the millions or billions of transistor is mounted on the single chip. Then after level of integration. So first of all, SSI comes. SSI means small scale integration, in which the few gates are used. 1 to 10 gates are used, like AND gate, OR gate, NOT gate. Example, early calculator and Bajit digital board. Then after medium scale integration, in which the 10 to 100 gates are used. It is used in the adder, multiplexer, encoder, and in the ALU and register. Then after LSI's large scale integration, in which the 100 to 1000 gate are used. It is used in the early microprocessor and memory chips. Then after VLSI, very large scale integration, in which the 1000 to 1 lakh gate is used. This is used in the and mobile microprocessor. And after ultra large scale integration, in which the more than 1 lakh gate is used, like today's CPU, GPU, AI chips. It is used in the like example NVIDIA, Intel, and AMD. As the level of the integration increase, the performance increase, size reduce, and cost per function becomes lower. So then after, what is physical design? So physical design, it is the process of converting the synthesized netlist into the physical layout. It is moving from the blueprint to actual construction of a house. It is determined the exactly where each cell and wires goes. So here looking in the diagram, so schematic design shows the logical connection of the gates and like NAND gate and OR gate. The netlist act as a intermediate data. We have netlist, net-oriented netlist, which list in the component are not specific wires, and pin-oriented netlist, which list wires connect of specific component pin. So basically, a netlist is a what is netlist? Netlist is a list of logic gates and their connections, which is generated after the synthesis. What is physical design decodes it decodes the exit position of the cells, like a routing path for wire and power and clock distribution. So why physical design is critical? Because circuit can be work at the required speed, no voltage drop, and chip can be manufactured without any failure. So this is the VLSI design flow. VLSI design flow, physical design is not an important step, but also a complex flow. It starts after the system specification, then after architecture design, and after once the circuit is designed, then we enter into the physical design. VLSI design flow explain the complete process of converting a data from the fabricated silicon chip. So first of all, we learn about the system specification. System specification basically determine the performance, power, and area. What area, how many area is used, and what powers are used in this. Architecture design divides the system into the major blocks like processor, memory, and interface. Then after function logic design. The function and logic design describe the behavior of the system using the RTL HDL language. We use the system Verilog and Verilog. Then after physical design is performed. Physical design convert the synthesized netlist into the physical layout. Then after we can see here such as partitioning, floor placement, tree, clock synthesis, signal routing, and timing clauses. So these steps describe the exact portion of the cell, clock distribution, and interconnection on the chip. So am I audible? Hello.
Yes, audible. Yeah.
Okay. As you finally, the design is fabricated in the semiconductor foundry, followed by packaging and testing to ensure the current operation of the chip. So that's about it. Once the physical design is completed, physical verification and sign off is done. This includes dynamic rule check and to verify the manufacturing, like a layout versus schematic, to ensure the layout matches to the net list, and timing verification. After that, verification layout posting processing is done. So finally, the design is sent to the fabrication to fabricate the semiconductor foundry by packaging and testing. Uh, so then RTL to GDS. So to simplify the VLSI design flow, we start with the register transfer level code, synthesize into the netlist, and then perform the physical design. Used to the output of the physical design, which should be in the GDS format, GDS file, which contains the complete layout. The state acts as an interface between the front end and back end. Like front end in the we use the logic, and in the back end we use manufacturing. Design flow like RTL then goes to the synthesis, then goes to the physical design, and then finally it fabricates. So, so what is the main objective of the VLSI physical design? The main objective is to reduce the chip area, and it used to reduce the chip area so that the faster in performance and less heating and easy wiring, so that and it should be passed with the dynamic rule check and layout versus schematic. Then floor planning. The first major step is the floor planning. This is where we define the chip size and shape. We decide where to put the macros and in IP blocks. This is critical because the floor plan leads to routing the congestion. So why this is important? A good floor plan reduce the timing problem and the routing congestion. So power planning. Power planning, next is power planning. We must design a network or VDD for the power and the VSS for ground that delivers electricity uniformly across the chip. As you can see here in this diagram, you can see the structure. We use the power ring go around the core, and the power stripe and gates run across the chips to prevent the IR drop, voltage losses, and the electromigration where the wire damage due to high current. Then placement. Now we move to the placement. Unlike macros, the standard cell are the much smaller and placed in the sides rows. Then it happens it in the two stages like global placement and the detail placement. In the global placement, like rough location, and detail placement, exact locations. So our goal is to reduce the wire length and improve timing and minimize the congestion. As so in the image, we add the specific cells like ends gap cells to protect the row end, and well trap cells to prevent the latch up. Then clock tree synthesis, CTS. CTS is the most important step for the timing. We need to distribute the clock signal to every flip-flop at the exact time. Before CTS, uh, the clock is connected to everything, but signal reach different flip-flop at the different timing. After we apply the CTS clock tree synthesis in the bottom image, as you can see here, mm, we use the structure the like H structure or balance tree. Here you can see the balance structure with the buffer to ensure the signal in the synchronized format. So let us go ahead. Routing and the physical verification. Routing is where the finally wires and cells together by using the different metal layers like metal 1 and metal 2. We must follow the strip spacing and enclosure rule to ensure the chip can be manufactured. After routing, we perform the physical verification. So physical verification means a dynamic rule check, ensuring the layout does not violate to manufacturing limits, and layout versus schematic, making sure the final layout must be matches with the original net list. Uh, then tape out and tools. The final physical design is in the GDS format as we have studied earlier. When we finish with the tap out, which means the design is ready for the foundry, the industry standard tool like Cadence we use, Synopsys, IC compiler, Mentographic, and Mentocaliber. This image here, as you can see, show the tool being used to a view of physical layout of the standard set, like showing a VDD, VSS, VDD, VSS, uh, and the metal layers and the diffusion layers. This image I have shown the metal layers and the diffusion layers. Finally, our conclusion is to basically uh, physical design. Basically, we can say the backbone of ASIC and the SoC design. It means is a critical bridge that run our logic to the silicon. So finally, while balancing the performance by power and yield. Yield is basically the yield can be defined as the good chip out of the total chip. Okay. So thank you, sir, for listening. Also. Thank you. Hello.
Yeah, completed, Manish. Good. Good presentation. Yeah. So from which college?
Sir, I am from Guru Gobind Singh, Indraprasth University, New Delhi.
Okay. Okay. Great. Great. So third year or fourth year?
Sir, I am in the third year currently.
Third year. Okay. Good. Appreciable. Very good. Yeah.
Okay. Thank you, sir.
Yeah. Next, who would